Okay, so let's have a look at another question, just like the one we've just done, in relation to which direction should a pilot head their plane in when they're trying to travel between two airports. So in this situation, we're told a pilot wishes to fly from airport A to airport B, which is 200 kilometers due southeast of airport A. A steady wind blows from a direction 60 degrees south of west at a speed of 50 kilometers per hour. If the aircraft can travel at 400 kilometers per hour in still air, find number one, the direction which the pilot needs to head, and secondly, the total time for the journey to the nearest minute. Now, as I said, this is quite a standard question that appears a significant amount of time in the exams. Generally, the airports are either due east-west or due north-south of each other, but from time to time, they do ask questions like this, where it's at some kind of an angle. So first of all, my instinct is to start drawing when I'm doing a question. So I'm going to begin with a situation where we're drawing a line from airport A down to airport B. And a nice diagram helps a lot. So there's airport A up there, and then due southeast, we had airport B down here. And then I'm just going to draw a reference line across here, because we know that if airport B is due southeast, that angle there must be 45 degrees. So that's the scenario with the airports, and this distance here is 200 kilometers along that black line. Now, the wind. Well, over here, we'll think about the wind. Right, well, the wind we know we're told is coming from a direction which is 60 degrees south of west. So I'm just, first of all, quickly drawing a north, south, east, west reference. So we have north, south, east, and west, and the wind is coming from a direction 60 degrees south of west. So that means that the wind is coming from somewhere down here at an angle of 60 degrees or from an angle of 60 degrees south of west. So there's the velocity of the wind vector, okay? Now, people always get confused about which vector is which in these questions. So just to be clear, let's go through an explanation. VW is straightforward. VW is the actual velocity of the wind. It's blowing at 50 kilometers per hour from a direction 60 degrees south of west. That's clear, okay? So that's VW. VA, that is the actual velocity of the aircraft. Now remember, we actually want the aircraft to go from airport A to airport B. So VA is going to point along that line, and let's draw that in red, okay? So VA, the actual velocity of the aircraft, is going to point down like this. That's what we want the aircraft to actually do, okay? To actually go from A to B. Now, the velocity of the wind, the aircraft relative to the wind, that is the velocity that the aircraft would have if there was no wind, if the second letter was stationary, okay? If the wind was stationary, if there was no wind, that's the velocity that the aircraft would have, okay? Now, a good way to start these questions is to begin by drawing the wind vector into your AB diagram on the left so that the tip of the wind arrow touches the line joining A and B. So I'm going to draw the wind in here. So the wind comes up here like this. The scale doesn't really matter. It's just a rough diagram to help me do the question. So I'm drawing it up in that direction so that the tip of the wind arrow touches the tip of where we want to go. Now, we know from the triangle law that if two vectors form adjacent sides of a triangle, nose to tail, then the resultant is the third side of the triangle. Now, we want the resultant to be where we actually go. So what the pilot would need to do is point their aircraft at the tail of the wind vector. So that's what the pilot would do. They would point the aircraft in that direction there at the tail of the wind vector, as we said in the previous question. So this one is the velocity of the aircraft relative to the wind. So this question here is exactly like the previous question we did. The only difference being that A and B are not north-south of each other or east-west of each other, okay? Now, what I need to find out really, I suppose, is I need to find out what that angle there is. Let's call it theta. Because if I can find out what theta is, I can add it to 45, and that tells me the heading of the aircraft relative to the wind. Now, what do we know? Well, we know that in still air, if there was no wind, the aircraft can fly at 400 kilometers per hour. So that means that this side here is 400. The velocity of the wind we know is 50. So the length of that is 50. Okay, now all we need to know is we just need to figure out one angle in this triangle. If we can figure out any angle in this triangle here, we're home and dry, because we can use the sine or cosine rule to find out whatever we want. Okay, now I think the best way to do this is to draw a line across here. Just going to draw a little line going across here through this point. I know that because alternate angles are equal in measure, that this angle here is the same as this angle up here. So that part of that angle is 45 degrees. And I know that this angle down, remember the wind is coming from a direction, we know this already. This angle down here is 60 degrees because that's the direction that the wind is coming up at. So that means if you add the 60 and the 45, you clearly get 105 degrees in that angle there. Now, there's no necessity to draw this extra picture, but for clarity's sake, I'm going to do so. So here is the first side, the VAW side. Then this one is the wind. And then this one here, let's go red again. This is the actual velocity of the aircraft. So this is VA. Now VA with no arrow on top means the length of that side. Well, not the length of it, sorry, the modulus of that vector. Now, so let's put in the other information. We know that this side here is 50 kilometers per hour. We know that this side here is 400. We have now figured out that this angle here is 105 degrees. And I'm trying to figure out what theta is. Okay, now all I need to do here is use the sine rule. And I can see very simply, I can find theta using the sine rule because I know the length of the opposite side. I know the length of the side opposite, which is 50. Okay, sorry, I should say the size of the side opposite it. So using the sine rule, the sine of any angle divided by the size of the opposite side, or the length of the opposite side, equals the sine of any other angle, sine of 105, divided by the length of its opposite side, which is 400. Now I'm looking for theta, so I need to keep this here on the left, and I need to get rid of the 50. So I'm going to multiply across by 50, and I get sine of theta equals 50 multiplied by the sine of 105 divided by 400, which tells me that sine of theta is equal to, so we grab our calculator and make sure we're in degrees mode. So 50 multiplied by the sine of 105 divided by 400 equals 0.1207. 0.1207, and then a whole lot more decimals. So then sine inverse button, and we'll find out what theta is. So second function, sine inverse that, equals 6.93 degrees to 2 decimal places. Okay, now very often the applied maths examiner doesn't say we want this many decimals or this many decimals. If they don't say anything and you decide to go for decimals, leave it at 2. Okay, leave it at 2, it's fine. So theta is 6.93. Now, what we were asked is, what is the heading of the aircraft? So let's have a look back at the picture. Now, as I said, theta is the angle to that red arrow in the diagram up here on the left. But the overall angle to the east axis, or the x-axis, is theta plus 45. So now we say theta plus 45 is equal to 6.93 plus 45, which is 51.93 degrees in a direction south of east. Okay, so that is the heading that the pilot would need to take, 51.93 degrees south of east. Okay, so that's part 1 completely sorted. The direction in which the pilot should head, done. Now we need to know the time for the journey. Now, what we do know is we know that these two airports are 200 kilometers apart. Well, what I need to know is I need to know the actual speed of the aircraft, the resultant actual speed of the aircraft, in other words, VA, so that I can use the fact that time equals distance over speed to calculate the time for the journey. So we're looking back at this triangle again. Okay, now we've worked out at this stage that this angle up here is 6.93 degrees. And that means I can calculate this angle over here very, very simply, because I know that the angles in a triangle must add up to 180. So let's go 180 minus 105, that large angle, and then minus the 6.93 as well. That gives me 68.07 degrees. And now I can very simply say, using the sine rule, that VA divided by the sine of 68.07, any side divided by the sine of the opposite angle, equals any other side divided by the sine of its opposite angle. So say 400 divided by the sine of 105. So VA divided by sine of 68.07 equals 400. Now just check I'm correct, 400 divided by the sine of 105 degrees. So that means that the actual speed of the aircraft, remember VA with an arrow on top means the vector, the actual vector velocity of the aircraft. VA with no arrow on top means the size of the velocity, in other words, the speed of the aircraft. So that's 400 multiplied by the sine of 68.07 divided by the sine of 105 degrees. So the actual speed of the aircraft is going to be 400 multiplied by sine of 68.07 and then divided by sine of 105. And that turns out to be 384.15 kilometers per hour. Okay, that's the actual speed of the aircraft. Now, again, we're sticking with 2 decimal places. Now, we were asked how long is the journey going to take? Well, we know that airport A and airport B are 200 kilometers apart. And we just calculated that the actual speed is 384.15. So the time for the journey is going to be the distance divided by the speed, which is 200 kilometers divided by 384.15. So the time for the journey is 200 divided by 384.15. And then remember that button that we use on our calculator, the answer is 0.5206 hours, but don't press cancel on your calculator. Go second function and then the DMS button, and that tells me that the time is approximately 0 hours, 31 minutes, and 14 seconds. So your calculator automatically changes that decimal 0.5206 into a time in hours, minutes, and seconds. Now let's read the question to see what accuracy they wanted. So find the time for the journey to the nearest minute. So we need to round to the nearest minute. So to the nearest minute, the time is approximately equal to 31 minutes. Okay, just be careful with the 14 seconds. Remember, normally we round up if it's smaller than 5 and round up if it's 5 or bigger. But there are 60 seconds in a minute. So you round down if it's less than 30 seconds and you round up if it's 30 seconds or more. But to the nearest minute, it's going to take 31 minutes to travel this journey. Okay. Now, I hope you all understood that. Okay. As I said, it's pushing the extent just a little bit. It's a little bit more tricky than some of the questions we've done already. But we're going to do a couple of these just to make sure that you know exactly what you're doing, particularly in relation to drawing the arrows. drawing the vectors onto the diagram here. That is fundamentally important. Okay, so let's do our next question.